Well, welcome back everybody to Auto 513. Today we're on session 4 and we're going to be talking about thin wall beams. So this is a very unique property of automotive sections. So we're going to introduce this subject today, kind of give a motivation of why thin wall beams are used in automobiles, and then at least start to do some of the derivations and understand the behavior of such beams. So what we're looking at on the screen now is a couple of beam sections. On the left-hand side is a kind of a typical automotive rocker beam, and you can see that the thickness is very thin. And on the right-hand side, we have a civil engineering beam, an I-beam, and it's kind of thicker. It's kind of a fatter beam, and we can quantify that thickness or thinness by a B over T ratio. So B just represents the kind of the overall width of the beam. So on this rocker section, it's kind of on the order of 100 millimeters or so, and the thickness is on the order of about a millimeter. So we have a B over T ratio of a 100. So the higher that B over T ratio is, the thinner wall section that we have. For a typical civil engineering beam, we have something on the order of about 10 or so. So you can kind of see the differences, and we have a way to quantify it. But the real question is, automotive sections tend to look like the one on the left, and why is that? Is it just because we use sheet metal as a material, and that's why? So what we're going to try to do is kind of get to the bottom of that, and we're going to start by using a thought experiment here. So we're going to be looking at a little cantilever beam here that you see at the top, and initially we're just going to say it's a square section. We know that's not very efficient, but that's going to be the starting point. And this little beam has a fixed length, and we're applying a load at the tip of this cantilever beam, and we're measuring the deflection. And what we're going to do is we're going to hold the cross-sectional area constant. So that what that means is that we'll be looking at beams of the same mass, so they're kind of on an equal footing. When we take the cross-sectional area times the length times the density, that's the mass, and we're holding all those things constant in this. And what we're going to kind of think of doing is we're going to vary the shape of that section. We're going to kind of pretend like it's, like it turns into to putty for a little while, and we can remold that material into a different cross-sectional shape, and then kind of wave a wand and harden it again, and then do the little test. And what we want to try to do is get the highest stiffness for this beam. So for a given load, we want the lowest amount of deflection. And we've already really developed the relationships in order to do this. The stiffness of this beam is 3EI over L cubed, and the strength given by the stress is equal to MC over I formula, ends up giving us this relationship. So the force is related to the design stress times the moment of inertia, and C is the distance from the neutral axis to the outer fiber, just as we talked about a couple of sessions ago. So when we look at these, we see both of these parameters are a function of the moment of inertia. So we kind of get some idea of how we want to make the changes here as we go forward. So again, we're going to kind of vary the shape of the same amount of material to get the highest stiffness. That's our little objective in this thought experiment. So here's what the starting point. We have this square section. We're just going to say that has a relative thickness of 1. That's the baseline. Okay. So from what we talked about, really in I think it was might be the first or second lecture when we talked about moments of inertia, we know that we want to get the material farther away from the neutral axis, which is right here, and that will make the beam both stiffer and stronger. So here is kind of our next kind of an idea here. So again, same amount of cross-sectional area. We've just moved it farther away from the neutral axis, and that gives us, in this case, a stiffness of 17 times the point that we started at. Okay. So this is, doing exactly what we want. And remember, we said we want the stiffest cross section. So let's kind of continue on. So here's another one. So here's the neutral axis, and we've just really moved a lot more of the material, really far from the neutral axis. And now this is got a stiffness of 115 times the base section that we started at. Okay, so we're really starting to get an idea of what should the shape of this beam be in order to maximize the stiffness, having the same amount of mass in it. So this is kind of like an efficiency measure. So once we're at this point, kind of the next step is, well, why don't we, even make this thing even higher than this, make it maybe paper thin. Okay, and kind of intuitively we know that we can't kind of continue this process on forever, that there is a stopping point. And what is that stopping point? We'll take a look at in a minute. But what we're looking at here is kind of the same thought process that happened back in 1845, where the engineers designing a bridge over a river. This is kind of the historical way to design these bridges in I-beam sections, but he went through the same thought process that we did, and he said, well, I'm going to take the same amount of material and I'm just going to make it into this really huge tall beam, and in this case here's a neutral axis, so he's putting lots of material way far from the neutral axis, just like we talked about, and he made the beam so big that he's going to drive the train right through it. And if we look at this, we can kind of see that here's the width of this section. Here's the thickness all the way around. So in this case, the width to thickness ratio is 390. So this is really the first structure that really got this idea of using these very thin wall sections with these really huge B over T ratios. And the reason for that is that they're very efficient, right? They're very stiff compared to the amount of material that we're using. But kind of there is a limit to this, and here we're going to start to talk about what that limit is. So here is now we're kind of testing this cantilever beam that we looked at before for a couple of different shapes. So this is the I-beam shape when we're looking at the load deflection, and right now we're looking at the linear elastic region, and it's behaving just as we said. Here's the slope of that curve. Here's the really tall, thin beam, same amount of material, and its slope is much greater, so its stiffness is much greater. So kind of the very rudimentary theory that we looked at before is holding here. But here's the difference. If we kind of continue to increase the load, what we would find is that the kind of stocky beam will have a much greater strength than our little thin wall beam. Okay, so we have a greater stiffness for the thin wall beam, but the strength is much lower. Okay? So we might kind of say, well, what's happening? Why is that? When we look back at our governing equations, we're increasing I for that thin wall beam, making it taller and taller. So as we saw, the stiffness is greater. But when we look at this second equation, well, it looks like the strength should be greater. It's proportional to the moment of inertia as well. Well, what's happening is that the design stress is really changing. Generally, we look at design stress and say, well, the design stress is the yield stress of the material, or maybe the tensile stress of the material, and if so, this should be increasing as we increase the moment of inertia. But what we're introducing with these thin wall designs is really a new mode of failure. And in order to see what that mode is, we have to kind of look at what's the stress distribution in the beam. And we're looking at a section kind of close to the wall here. And as we talked about in the second lecture on beams, we know that when we put a load downward like this, the top portion of the beam is going to be in tension, and the bottom portion of this beam is going to be in compression. And what we're going to see in thin wall design is that we have a new failure mode, and that is thin plate buckling of the compression elements. So whenever we have a section that's thin walled, made of plates, and those plates are in compression, it can buckle by going into this kind of wavy shape. And we have to kind of contend with that. And let's give kind of an example of that so you have a feeling for what we're talking about with plate buckling. So what you're going to see in this little video that I'm going to play, it's a couple of hat sections that are welded together here, and I'm putting a bending moment in this direction. So this top plate is going to be in compression. So we're just going to consider this this top plate, just one element of this beam that's very thin-walled, and you'll see it kind of pop into this state of plate buckling right there. Let me stop oops, it stopped it too slow. Let me stop it. Boom, there. So you can kind of see that top plate all of a sudden became very wavy. It's kind of like a series of sine waves from one end to the other. And that is kind of a new failure mode that we didn't have before. This occurs at a stress often below the yield stress of the material. So it's kind of a new failure mode that we get in these very stiff structures that are thin-walled, but we have to contend with this new failure mode. So let's kind of just look qualitatively at how does this new failure mode behave. So what we're plotting here is the design stress, and it could be yield, it could be this buckling phenomena that we talked about. And what we're going to plot it against is the B/T ratio of the plate. So what we've done is on this little chart here, we've just taken one plate and we have simply supported boundary conditions on all the sides, and we're applying a compressive stress. The plate width is B, the thickness is T, and it's very long, so we don't even worry about the dimension here, just very, very long in expanse. And we're plotting on this little chart design stress versus this width to thickness ratio. So the first one that we kind of all presumed is that we have a design stress of yield. So when we reach yield, we say that this plate is in some sense failed. But what we're going to see in the future now is that we also have this plate buckling stress, the stress at which this plate would buckle. And it's a function of the B/T ratio squared. So that's why we're plotting this against B/T here. And we'll kind of justify this formula a little bit later on, but just for now, just accept that this is the behavior of a thin flat plate. So the higher the B/T ratio, say 150 here, the lower the plate buckling stress. Okay? And of course, when we design this little plate, we want to be, the failure, the design stress will be whatever's lower. It's either going to be yield stress or this plate buckling stress. So let's just superimpose that again. So whenever we have a design and it kind of goes in up above the white area of this chart into this red area, that plate would fail. It can fail by one of two mechanisms. One is yield, the other is this plate buckling phenomena. And when we overlay these for mild steel, mild means the yield stress is about 200 newtons per millimeter squared. Then that kind of inflection point here is 60 B/T ratio. So below 60 will fail in yield. It's a kind of a stocky plate. It's kind of a thick wall plate, we would say. And above 60, it would fail by this plate buckling mechanism. Okay, so just let me caution you that the 60 is only for mild steel. We'll kind of see how it varies when we use other grades of steel that are higher strength. So this is the behavior of a flat plate and in the failure mechanisms, and that determines the design stress. So that stress is either yield or plate buckling, which is the lower. Okay, so we pretty well understand the idea of yield stress. What we're going to do in this lecture is start to talk about this idea of plate buckling stress and how do we handle it. Okay, so in the previous slide, we're just looking at a single flat plate under a compressive load. And there's not too many pure flat plates in the car body. The flat plates that we're talking about are really elements of a section. So here is just kind of a made-up thin-walled beam section here, a few plates that are welded together. But we want to think of that section as being made up of several plates. So here, this little top plate here we want to look at that as a plate. It has a certain B, it has a certain T, so it has its own B over T ratio. So for this little beam section here, we're ending up with 1, 2, 3, 4, 5, 6, 7 plates that we want to contend with. Any one of those plates can potentially buckle if it's in compression. Okay, so if we have a state of loading in this little of a beam here that's in pure compression, so the compression forces are compressing every one of these little plates, any one of them can fail in this plate buckling phenomenon. If we're pulling on that beam made up of all these plates, none of them will fail by plate buckling. Right? Buckling is a compressive failure. It gets more interesting when we're applying moments. So here's a moment in the counterclockwise direction that would put everything below the neutral axis into compression. So only those plates might buckle by plate buckling stress. If we reverse that, now only the ones above the neutral axis might fail by plate buckling. Okay, so I just want to make sure that even though we're talking a lot about plates kind of in isolation, really we're eventually want to look at these as plates within a automotive beam section. So let's just kind of say, well, when would you want a thick wall section? When would you want a thin wall section? So here is kind of a generic thick wall section, has a low over B over T. We saw that these things have very high strength because they fail by yield, but they have a lower stiffness. They have a lower moment of inertia value for a similar weight. Here is a thin wall section properties that we're looking at. It has a greater slope because it has a higher moment of inertia. We're using the material a little more effectively for stiffness, but it has a lower strength. So the value here is dropped down, and it fails by buckling. Okay, so we would choose a thick wall section. If strength is really important to us and stiffness is not so important, we would choose a thin wall section if stiffness is really important and strength, not so important. Okay, so that's the way that we would judge which kind of a section to choose in general. This is very qualitative. So the real question is, we're not designing generic beams; we're designing beams for automobiles. So let's ask the question. What kind of beams would we want in an automobile? Should they be thick walled? Should they be thin walled? And we're just going to take a particular example here of a rocker or sill section of this little convertible. So we've kind of thrown away the roof of the car just to make this kind of a simple little exercise to look at. The length of the rocker section in this little example is 2,500 millimeters, kind of roughly, typical car size. And we have some requirements for the body structure, strength and stiffness. We have these two requirements. They're really independent. We can vary strength, we can vary stiffness. We'll justify these values, but these are what we're going to use right now. 6,680 is a strength requirement, so we'll want to put a load of that magnitude on the car and have it just ready to fail at that load. Okay, so that's the strength requirement. We also have a stiffness requirement for the body of 7,000 newtons per millimeter. So that kind of constrains the amount of deflection of the little beam here as we apply that load. So again, just accept these for now. In a subsequent lecture when we talk about body bending, we'll kind of justify why these requirements make sense. So in this little exercise we're going to isolate that rocker section. We're going to just look at one side. We're going to be loading it at the center span. It will be deflecting under that. So we already have the equations for this little beam. And we're going to say just kind of arbitrarily that we have a width of that beam that we want to specify. The height of the beam we'll just take as a fixed value. It's going to be 1.5 times whatever we select for the width of the beam. Okay? So the proportion of the beam will be fixed. And the other variable that we'll have to select is the thickness of the beam. And we're going to take these requirements and divide by 2 because we're looking at just one half of the car and maybe the left side we're considering here. So these are now the requirements on this little beam. Okay? And kind of what we're going to do here in this little exercise is we're going to determine B and T that will minimize the rocker mass and yet still meet the 2 requirements that we've set up. Okay? And we don't even know if there's a particular solution for this yet. It might be a wide range of things, but we're going to kind of say, well, what is B over T that minimizes the rocker mass? And then from that, we'll see, well, did we end up with a thin wall section? Did we end up with a thick wall section? Okay? That's really kind of what we're after here. So here we can plot this kind of on a requirements graph here. So this is the strength requirement that we're looking for. This is the stiffness requirement that we're looking for. Any structure that we kind of invent has to fall into this green region in order to be acceptable. If we have a design that's falling out here, that is not strong enough, it's not stiff enough, so that's not a viable design. Right? So this is kind of the idea of where we're going with this. And I'm going to go rather quickly through these this little development of the equations that I'll be using as we do this. So you might need to kind of pause the video as I go through this, knowing that I'm going to kind of just go through this quickly. So again, nothing new here. We can look at the little tables that we looked at a few lectures ago. This is the stiffness of a simply supported center-loaded beam. This is one of the quantities that we're going to be interested in. We know this from the second lecture, I think, sigma is equal to MC over I. The maximum moment for a center-loaded beam is given by PL over 4. So that would be right there. That's where the beam will fail. So we can solve this for P. So we can say that the strength P max is given by this relationship, and for sigma, we said, well, that's going to be the design stress. Okay? And now we know for this kind of a case that we have two possible design stresses. We can either fail by yield or we can fail by buckling. Okay? And I've kind of written an equation here with a constant divided by the B over T ratio squared. And again, we're going to justify this equation a little bit later on, but we're just going to accept this as the behavior before. So this, if we plotted this out, this would look like that chart that we looked at before as the design stress. Okay, and whatever is the minimum of those two quantities, that's what we will choose. And we're going to take yield as being a mild steel for right now in this little exercise. So this is the chart. So whenever we're at a B over T ratio of less than 60, we're going to fail by yield. Whenever we're above 60, we'll have to use this relationship here to establish what is the design stress. Okay, so either by failure by yield or by buckling. Okay, so here's the two equations that we were looking at. So if I know we're going to use steel, we have a certain constrained length. We said that was going to be 2,500 millimeters here. C is half of the height of the beam, so we know that. Here is the proportions of the beam that we're going to be using. So the cross-sectional areas is something that we need. So we're just taking the perimeter, the distance here. Here's B, and then we go up one wall here. That's the 3/2 B. We're going to multiply that by 2 because we have the other side of the beam. Multiply that by T, and then we have the cross-sectional area. And we're going to just kind of change that a little bit in this little example here into this quantity that I've shown there. So we can solve this for B. So we can pick a B, height of this or width of this little beam, and from that we can relate it to the cross-sectional area of the beam in the B over T ratio. Okay, so it's kind of a peculiar formulation, but this is going to help us solve things. So this is just taking that equation, solving it for B. And then equation 4 that we're going to be using, it's kind of a nonsensical equation. It's just saying that the thickness is equal to B divided by the B over T ratio. And the reason that we're doing this in this peculiar way is we're going to say this is going to be an independent variable, something that we're going to vary. And the cross-sectional area is also going to be an independent variable. So we'll pick a cross-sectional area, we'll pick a B over T ratio. From that, we can calculate a B and a T. Once we know that, we can calculate the moment of inertia and then solve these two equations. So that's kind of where we're heading. So here's the solution steps that we'll be using. And first of all, we're going to choose a cross-sectional area. So that kind of tells us how massive is the beam. That determines the mass of the rocker. And then we're going to choose a B over T ratio. And the reason we're using this as an independent variable is that if it's below 60, we know that the failure mechanism is yield. If it's above, we know the failure mechanism will be plate buckling. Okay, so we'll be able to kind of look at beams like this. So whenever we have a small B over T ratio, it means kind of a squat beam that looks like this, very thick, and it will fail by yield. If we have a large B over T ratio, it will be taller because we're using the material, putting it farther away from the neutral axis, and we know that it will be fail by plate buckling. So once we've selected an A and a B, then we can use these equations, or B over T, excuse me. Then we can solve for B, we can solve for T by using those equations, and then we can solve these equations for the stiffness and the strength of the beam. Okay, so this is kind of where we're heading. So just an example calculation, and then we're going to go off to a spreadsheet that actually solves this for us, so we can really kind of more concentrate on the thought process of what's happening in this case. So here we're choosing a cross-sectional area of 500 millimeters square. We just kind of picked that out of the air. We're choosing a B over T ratio of 10, so we know this is going to fail by yielding. So we can solve for B. What will this be for these two parameters? So we use this equation, and we come up with a B would be 31.62. And then we can use the equation 4 to solve for what would the thickness of the beam be. And here is that value. So now we've specified the cross section in this case. Now we can solve for the moment of inertia. It's just a function of the height of the beam, which is 3/2 B, and the width and the thickness. So we can come up with a particular number for that. And then we can plug that into the stiffness equation. It's shown here. We have a stiffness of 107 newtons per millimeter, and we can put it into this equation, and we can come up with a strength for that beam. Okay, so these are the steps that we're going to be going through. And now we can take this value and say, well, how does that particular beam fare on meeting the requirements that we have? Okay, so here is the strength that we calculated, the stiffness, and here is the performance of that particular beam. Okay, and it's pretty crummy on this. It's nowhere near coming into the acceptable region. Okay, so what would we do? Well, one thing that we can do is say, well, we just have to have more material in the beam in order to start to get it to fall in that region. So we might increase the cross-sectional area in order to start to make the beam meet that acceptable zone for both stiffness and strength. Okay, here's another one. Here's using the same cross-sectional area, but we've just changed the B over T ratio from 10 to 40. So we still have a thick wall design that will fail by yield, but it has a higher B over T, which means it's a little bit taller, and it has better performance. Right? Now we actually are meeting the strength requirement, but we still have a gap to the stiffness requirement. Okay, so I hope you understand kind of the model that we're looking at here. And what the reason we're doing this again is to kind of convince you that the optimal section will be a thin wall section for this little a convertible example that has very realistic kind of requirements that we're trying to meet. That you know, if we want mass efficiency, the best way to do it is not with a thick wall section. It's with a thin wall section. So what I've done is I've programmed those equations in Excel for two cases. One is by failure by yield, so that will be for B over T is somewhere between 10 and 60, I think I used. And then another model that will fail by plate buckling, and for that one the B over T ratio is greater than 60, and I think it might go up to like 300 or so, so very thin-walled. So what we'll want to know is where, you know, what proportions of that beam, thick or thin wall, will give us the most mass efficiency. Okay? So I'm going to jump out of PowerPoint here and go into the first model. So here's the one that has a failure by yield. So we've selected the properties are for steel, modulus of elasticity, the yield stress about 207 in this case, so that's a very mild steel. The length of the beam, like I said in the little setting up the problem, 2,500 millimeters, and strength requirement 3340, and the stiffness requirement 3,500. So that's what we're trying to do. So here's a chart that we were looking at before. Here's the beam strength, the stiffness, and here's the region that we're trying to jump into. And here's a little scroll bar here, so I can change the cross-sectional area of the beam. Okay? So some beams will just be too kind of skimpy. We just don't have enough material, and we'll just have to keep adding material until we get into the region of interest. Okay? And then what you see at the bottom are some B over T ratios that are kind of inputs again. So 5, 10, 20 in increments up to 60. And then from the area and the B over T, we calculate a B, calculate a T, and then we can use those same equations to calculate the stiffness and the strength. So this is the same calculation that is just automated right now. I have zero area, so we have essentially no beam right now. So let's just add some cross-sectional area here. Okay. So what you see on the chart here is like a little worm here, and these are we have 2, 4, 6, 7 different solutions here, 7 different beams from a B over T ratio of 5 all the way up to 60. The one at the top is 60. Right? It's the tallest beam. The one at the bottom is the one for 5. And you can kind of see that with a cross-sectional area of 169, we don't have anything entering the solution area here. So the beam just isn't big enough. It'll never work no matter how we proportion it. So we have to keep on adding material, and as I do that, you kind of see the little worm getting bigger and bigger. And so here we can actually see the distinct points for each of these B over T ratios. And I'm going to just tweak a little bit more because we're almost at a level of having adequate strength. Okay, so we're shooting for a strength of 3340, and right now this is saying that for the B over T ratio of 60, we actually have a strength that exceeds the requirement, 3357. And in that case, we have cross-sectional area of about 348, and the mass for that two steel rockers is about 13.6 kilograms. Okay, but we're only meeting one requirement. We're only meeting the strength requirement, and we have a long way to go this far before we get into this zone to meet additionally the stiffness requirement. Okay, so just kind of remember this 13.64 thick wall meets the strength requirement. So I'm going to kind of really go through this quickly, adding more and more mass, making the area bigger and bigger until we finally get into that zone for both strength and stiffness. So almost there. And then finally here we go. Oh, there we go. I think that's pretty good. So this one, we're now at 3520 for the stiffness, and we wanted 3500. So we have adequate stiffness. But look at the strength. It's at 20,600. So far exceeding the strength requirement. but it's the first thick wall design that actually meets both requirements simultaneously. And it has a mass of about 45.8 or so. So we really had to go a long way in order to additionally meet the stiffness requirements for this beam. Okay. So let's take a look at that, just to kind of sit here for a minute. So here we had a design that met the strength requirement, but not the stiffness. It was showing 13.5 here. Here was the other design that weighed 46.6. It shows here it met both requirements simultaneously. Okay? So this is the best we can do with a thick wall design that will fail by yielding. Okay? Not really too good. So what's going to happen next is we're going to look at thickness ratios above 60, where we're going to allow additionally the design to fail by yield or plate buckling as well. So kind of here's the performance that we were looking at up to a B over T of 60. The curve kind of looked like this. It had this general shape. But now we're going to go beyond 60, and what we're going to see is that we have kind of a curve that comes down like this. So this is what we're going to be seeing, and again, we're going to want the performance to fall into that region. So it's not really clear what in the heck we're doing here. We actually have now, we've reached a peak here for the strength, and we're starting to get weaker and weaker, lower and lower strength with the design. So it kind of looks like a nutty idea on the surface, but let's kind of see where it takes us. And I'm going to kind of jump out here again and go into a different model here in Excel. Everything is the same, except now you see this region here in blue, which is for B over T ratios above 60, which now is where we would fail by plate buckling on that top cap. Okay? So we're starting off at the same point here. We have 0 cross-sectional area. So let me just zip this over. So we're seeing that general shape that we looked at before. So failure by yield up to this point, and then above that we're failing by plate buckling. And here we have B over T of 60, 70, all the way up to some really pretty high numbers here. But this goes in increments of 10. So again, we're trying to get into this region here. So let's do this quickly here. We're starting to get really close. There. So we have a solution here. We just kind of zipped into this acceptable region for both stiffness and strength. And it's obvious that it's going to be a thin wall design. That's the kind of winner of the contest. I can just kind of count. I know these are in units of 10. So B over T of 60, 70, 80, 90, 100, 110, 120, 130. And then the next one is 140. So the winner is kind of a B over T ratio of about 135 for this particular design. And the mass is 30.56. Okay, so let's go back to the PowerPoint and kind of regroup here at what we've learned. So this was the one that we looked at first. Failure by yield met strength but not stiffness. So this really we would have a car that would be strong enough so when we put all the load on it, it wouldn't fail, but it would be really sagging quite a bit, so it wouldn't be meeting the stiffness requirement. Here's the one that met both simultaneously and was thick wall, and here just kind of look at the mass. That's 45.6 kilograms, the first viable design, and then the one that failed by plate buckling was 30 kilograms. So we're kind of saving the delta there in mass is something like 15 kilograms. Quite a difference between the two. And all we're doing is reshaping the section, and what we're doing is kind of matching the performance of the section to the combined stiffness and strength requirements that we're looking at. So here is the region that we looked at and the optimal to get in there was a thin wall design, and you might say, well, you tricked us. You kind of just pick these requirements because it'll always lead us in that direction. But the solution always won't be a thin wall design. If we pick a different kind of proportion between the strength and stiffness requirement, and this is more in line with what we might see in the requirement of a building, say an I-beam holding up the ceiling. Typically in civil engineering structures, they can deflect more than what we are looking for in an automobile. So if we have these requirements rather than the ones that we looked at for the car, then the optimal solution won't be a thin wall design. It will in fact be a section that fails by yield. So this whole idea of that the ratio of the requirement for strength and the requirement for stiffness for a particular structure really determines the kind of requirements that you'll have. So let's kind of just look at this a little bit deeper here. So what do we mean by strength? Strength is a maximum load, and generally it's extreme applications where some permanent deformation or damage is expected. And so it's either going to be yield, where it's permanently sagged, or this plate buckling phenomena that we want to avoid. Stiffness is a completely different quantity. We can vary it, totally separate from the strength. So we don't always, when we have high strength, we don't always have high stiffness. These are two independent quantities. So this is a load per unit of definition. Usually it's in normal or repeated loading, and it's generally elastic behavior. And so here's a couple of different components. Here's component A, and this is the desired load deflection curve that we have. So in this one we have a required stiffness of 900 newtons per millimeter and a required strength of 2,000. And here's another component, a B here, that has a required stiffness of 10,000 and a required strength of 10,000. So you can kind of see the ratio between the strength and the stiffnesses are very different for these two quantities. And if we were to plot on a chart like this, what is the strength requirement, what is the stiffness requirement, if we're in this zone here where we have very high strength required, not so high stiffness requirement, we'd call that a strength-dominated design. If we were down here where we are requiring a very high stiffness but not so high strength, we'd call that a stiffness-dominated design. And for component A and B here, we're in kind of two different regions. One is in the strength-dominated area. Component B lies more towards the stiffness-dominated area. And what we just saw is that whenever we have a strength-dominated design, that will tend to lead us to having a thick wall proportions for the section and a yield by failure. Whenever we have a stiffness-dominated structure, we'll tend to have a thin wall solution, and it's going to fail by plate buckling. Okay? So this kind of the region here, whether we're high or low on this chart, will tell us the best proportions for the structure. And then the question is, well, we're designing cars here. Where do the different components fall on this chart? And generally, you'll see that they do fall in the stiffness-dominated region, so that we'll end up with these very thin-walled, kind of delicate sections are the best and optimal solutions. There are some exceptions. The B-pillar with lateral loading kind of from the side, so that would be for side impact. That tends to be a strength-dominant design, so that ends up being more of a thicker wall solution than some other areas in the car. Okay. So the whole point of this kind of a qualitative walkthrough here is to kind of convince you that there's a real significant reason why we're using thin wall sections in auto design, and it has to do with the ratio of what's the strength performance that we're looking for, what's the stiffness performance that we're looking for. So typically in transportation design, whether it's automobiles or airplanes, they tend to emphasize the stiffness requirements. And again, we'll justify those requirements in a lecture when we start to talk about bending and torsion. Good. So just to summarize where we've been, much of the automotive body structure is dominated by the stiffness requirements. A mass-efficient way to design for those is to use these thin wall sections that we saw. And a new failure mode of these thin wall sections is buckling of the compression elements. So what we want to do next, and we're just going to start this in this lecture and then we'll kind of complete it in the next lecture, is we need to understand what are the governing equations for some modes of this of plate buckling. How do we actually calculate these quantities? So before I just said, well, just trust me, this is the relationship for plate buckling. It's a function of this B over T squared. So the thinner the section, the lower the T relative to the thickness, the lower the buckling stress will be as we go in this direction. These are the kind of just graphically the proportions that we'll see on the sections. So where does this relationship come from? So we're going to start on that little journey right now, and it's actually a pretty complex derivation. So what we're going to do is look at a simpler case, and then by analogy, we're going to kind of extrapolate that to the plate buckling case. Okay, so many of us have looked at in our undergrad years at Euler beam buckling. So the famous hacksaw blade, you push on it, and at some point it buckles. Okay, now that's not plate buckling, but it's an instance of bifurcation. Bifurcation means two modes. So the beam goes from being straight, that's the first mode, to being buckled kind of instantaneously. So beam buckling, which is the Euler beam buckling, is an example of bifurcation. Plate buckling is as well. The plate goes from being a perfectly flat plate, being loaded in compression, to instantaneously it turns into this kind of ripply shape. Okay? So what we're going to do is derive the expressions for this simpler case, which really isn't the one that we're ultimately interested in, and then by analogy, we're going to develop the solution for the plate buckling case. Okay? So I'm going to show you, these are actually two little videos that I've scribbled all over. So let's just see the difference just to make sure that this is set in our mind. So this is a hacksaw blade. I'm going to push compressively and then goes from straight to boom into this half sine wave shape. So this is a beam buckling phenomena. Okay? So we're going to derive equations for that situation and then by analogy apply it to plate buckling, and ultimately this is what we're interested in. The plate goes from being flat to boom, this kind of a ripply shape. Okay? Okay, so here we are. We're starting our derivation here. Oops. Go get out of that. And into plate buckling. Okay, so here's our little buckle beam here, and we've added a coordinate system on it. So we have a x along the length and a y kind of perpendicular to the shape there. It has a certain L, and here's a load at the end. And when that load is low, it just reacts the loads directly. It maintains a straight shape, and at some point it kind of goes into this buckle shape, and we call that the critical beam buckling mode. We're not in the plates yet. We're still looking at this little beam. So here we go with kind of finding out, well, what is the lowest load that will cause this this beam to snap over into this half sine wave. So like we do with most beam problems, we kind of just take an arbitrary cut of the beam here. We throw away this half of the beam, and now we're looking at what are the internal loads being applied by this half that we've thrown away. So we have a bending moment here, and we have a compressive load being applied. Okay, and just note This is a positive moment that we're showing because it's beaming, it's bending the beam, so it's concave upwards. So here we have a negative y deformation. We don't know what that is yet. So let's kind of continue on here. So we're going to put this into static equilibrium. So we're going to take moments around that point. So we have the moment being applied at that point. We have this load going right through the point. So this load doesn't have any moment about that point. But over here we have the load P. We have it at a distance of minus y. That's this distance here. And it's going in a direction opposite the moment here. So that's why we have that minus sign. Okay? So we do just a little bit of algebra, and now we have that moment is equal to minus y times P. Okay. Now we're going to go back to the beam equations. So I think it was in session 2 we developed this relationship. Y double prime is equal to m over EI. So we're just replacing the m into that equation, and then we're solving it and setting it equal to 0. So basically we just get rid of that, and now we have this relationship. Y double prime is equal to minus P times y divided by EI, and we're just solving that so it's equal to 0. Okay? So this is a differential equation. We have y double prime and we have a y, and we need to kind of determine, well, what is the shape y that will kind of satisfy this equation. Okay? And if you remember from differential equations, one of the techniques is, well, you just kind of guess the answer and then see if it works. So we want to guess at a shape. Y is a function of x. That basically defines the curve. So this is y is a function of x. That's the shape of the buckle beam that will satisfy the differential equation that we just determined. Okay? So what's a good guess? Well, we don't have to be too creative. We can just look at that and say, boy, that looks an awful lot like a half a sine wave. So let's take that as a guess. So y, it's some amplitude. We don't know the amplitude of the sine wave. But all of this rigmarole just says that it's going to kind of look something like this. If this is the length. When n is equal to 1, if n is equal to 2, it will look like that. If n is equal to 3, it'll look something like that, and on and on and on. N can just kind of go on. Okay? So we're saying kind of generally we're going to make this, we don't know what n is for now, but we know it's a sine wave. Okay. So let's, we look at our equation. Well, one of the things we need is the second derivative of that with respect to x. So here is y. So here's one derivative. We're just kind of bringing what's in the sine function out there. The sine turns into a cosine, and then the second derivative, the derivative of cosine is a minus sine. So that's why we have this. We bring this out here again. That's why we get the squared. So now we can substitute that into this equation. And we get this relationship. So this is all this right here is the second derivative, and then we just take y and substitute that in there. So here's the P over EI that's there. Okay? So just substitution at this point. And so we can kind of group terms. So we're taking the a's from each side in this. The signs from each side, and we get this quantity here. So this is here, that's there, times that. And this has to equal to 0. And when we look at that, we said, well, sine of n pi x is not always 0. We can pick any x value here, and it won't necessarily be 0. So that means that this has to be 0 in order to satisfy that equation, because the quantity has to be equal to 0. So here's what we kind of determined at this point. That has to equal to 0. Remember, what we're really interested in this whole kind of derivation here is, what is P, what is the load that causes this buckling behavior. So here it is. So it's a function of n. Remember, n is the number of half sine waves in the deformed shape. So what we're always interested in, what's the lowest value of P that will first cause this beam to buckle, and that again is, the lowest value would be 1. N can be 1, 2, 3. So as we go to 2 and 3 and 4, P goes higher and higher and higher. So the lowest value would be for N is equal to 1. So here, the P becomes a critical buckling force for an Euler beam. So again, this is Euler was the guy that first figured this out. So we've got a solution for the beam. Okay. So let's kind of take a look a little deeper into this. We have a solution. We had assumed the deflected shape here, and we kind of just looked at the little video and could say, well, sine looks pretty good. But it had to satisfy a little more than the general shape. It had to also satisfy some boundary conditions. Okay? And boundary means kind of the edges of the structure that we're looking at. And in this case, we had two boundary conditions that we had no deflection at either end. So at this point here and at this point, we said that we can't have a solution that looks like this, right? This has to be equal to 0. Okay, so we have to make sure that that's satisfied. Y in this equation, when x is 0, has to equal to 0, and in that, obviously that's true for a sine function. If we put in y is equal to L, or x is equal to L into this equation, it's also equal to 0. And it doesn't matter what n is, it's always required. So this is satisfied here, even though we hadn't really looked at it before. And the second boundary condition is that we have no moment at either end. Okay? So we just have a force here alone. We're not doing that at the ends, right? My fingers, as I pushed in, were kind of too fleshy to apply a moment, so the moment has to be 0. And that's at the same positions at, this should be at x is equal to 0 and x is equal to L. Yeah, this. Okay, so from the beam equations, we have m equals a y double prime over EI. So what we're saying is when we have no moment at either end, this has to be equal to 0. So what we have to do is take the second derivative and make sure that it is also 0 at the edges, at the ends of the beam. Okay, so when we put in, here's y double prime, this has to be 0 at either end of the beam. So when I put in x is equal to 0, then this does equal to 0, so that's fine. And when I put in x is equal to L, it's also 0. So we kind of, without really knowing it, we kind of satisfied all the boundary conditions. Okay, we'll have to do this with the plate as well. Okay, so here we're going to kind of just summarize what did we do with a buckle beam, and then on the other side of this slide, we're going to start to look at a buckling plate, and then kind of by analogy, just kind of make the connections rather than kind of going through a pretty gruesome derivation. So the first step was we had to derive a differential equation for the beam behavior. Okay, and these were the values that we had to look at. And if you think back to the very first lecture, we talked about continuity and compatibility. We had to have equilibrium satisfied. That's basically how we got this equation. And compatibility and constitutive satisfied, that's how we got this equation. Okay? So that's where they came from. And then these gave us a governing differential equations. This is, I've kind of written this out full here. This is y double prime. We got a governing differential equation. Then we guessed at a deflected shape that would meet the boundary conditions. So that was this value. And then we substituted this deflected shape into this equation. We took two derivatives, substituted in there, and we got an algebraic equation. And then we made an observation that the sine function generally isn't always 0, so it couldn't be the one that's causing this equation to go to 0. It has to be the terms in brackets. So when we set that equal to 0, we can come up with the buckling load. Okay, so that was for a buckling beam again. Okay, now we're going to tackle the harder problem of a buckling plate. Okay? So here's our plate up at the top. This script F, this is the stress. So this is the compressive stress that we're applying. So this is kind of like the P. And if that F sub x is low enough, the plate's not buckled. If we continue to raise it at some point, the plate will snap over into this Ripley shape, and we want to know what is the lowest stress that will cause that plate to buckle. So that's what we're trying to figure out. And we need some dimensions for our plate, so we're saying, well, the loaded edge is going to be B units wide, and then for the length of the plate, that's going to be A units long, and it's going to, of course, be T thick. Okay? So we're not going to drive these equations because they're quite complex. If you're interested in a solution to those, here is a reference for you to take a look at. We're just going to state what these are, and it's the analog of these differential equations here. So here is the situation that we're looking at. All along this edge, this is simply supported. So it's kind of like a hinge all along this dimension, that dimension, that dimension, and that dimension. Okay, so that's the boundary conditions that we're looking at. Here we're showing the dimensions of the plate. We're putting the plate in the XY plane, and the axis perpendicular to that is the z-axis, and it's also the deflection out of plane. So W is if the plane moves up and down into this Ripley shape, W is the dimension that it moves. So here's a point here initially in the flat plate at coordinates x and y, and once the plate buckles, that point's going to move up an amount, W, and that's a function of x, y. As we move around the plate to different areas, we change x and y, that W, of course, will change. So here is the ugly equation. That's that differential equation. And let's just kind of talk it through. It's really not as intimidating as it looks. First, we have a bunch of quantities that are equal to 0. Secondly, in that equation is the applied stress. D is the plate rigidity. So it's down at the bottom here. So D depends on Young's modulus, the thickness of the plate, and Poisson's ratio. Okay? So the important thing here is, once we pick a material, D is just a number that depends on the thickness of the plate, primarily, and some material properties. Okay? So what else we got here? We have a bunch of derivatives. So what this is saying is that this plate is going to be buckling in some shape, W. We have a two-dimensional problem here, so W varies with both x and y. So this is saying if we kind of guess at a W function like we did with the buckling beam, that we take 4 derivatives of it with respect to x for this term. With this term, we take 2 derivatives with respect to x of that W function, and then 2 with respect to y, and multiply it by 2, etc. So we're just kind of really just taking derivatives of a function. There are some boundary condition constraints, so that if we look at the edges of the plate here, the moments must satisfy these relationships. And again, they look intimidating, but again, it's just taking some derivatives of whatever we assume for the deflected shape. Here's that plate flexural rigidity again popping up. And what you see on the right-hand side is just the definition. So we have something called an M sub x. So that is given by this. It's the moment that's being applied to an x surface. So here's a normal vector here to a surface that's in the x direction. So that's why this is called mx. This y, here's a surface here that's the normal is in the y. So here we have a m sub y here. And then we also have kind of a twisting moment here, m sub xy. Okay. So these equations have to be true anywhere in the plate. So here if we have an xy value, these equations have to be satisfied for the plate, and particularly on the boundaries, on the edges of the plate. Okay, so now we're kind of moving down here. Here's our differential equation that's very similar to this for the beam. And our next step is to guess at a deflected shape this time. So now we don't have a kind of a one-dimensional beam, we have a two-dimensional plate. So what kind of a solution are we going to guess there? So to kind of help us think of that, let's look at this video again. And I'll stop it right there. And so what we see across the beam is kind of like a half sine wave. And along the beam, we have a series of several half sine waves going along the beam. So just by that observation, it looks like the solution here is to, let's guess something that looks like this. So here's just an amplitude. How big is the deflection in general? This is varying with x. So this is kind of like the sines going along the length of the plate. And this quantity is varying with y, so it's like the sines going in the other direction. Okay, so on the right-hand side, we kind of show some examples of what does this function look like. And you can kind of see it depends upon m and n. We saw those in the buckling beam. These are just integers, 1, 2, 3, and they're the number of half sine waves that are occurring. So here we have an m is equal to 1. That's 1 half sine wave in the x direction. N is equal to 1. In the next picture here, we have m is equal to 2 half sine waves in the x direction. N is equal to 1, the number of half sine waves in the y direction. Okay, and you can kind of visualize that m and n can kind of keep going higher and higher and higher, and you get more complex behavior of the plate. Okay, so this is our guess, and we saw from the little video it's a pretty reasonable guess. So we saw from the beam buckling that we had to satisfy the boundary conditions. So let's see if this expression satisfies the boundary conditions for the bending moment. Okay, so let's kind of think about what kind of boundary conditions do we have. So boundary conditions are always just we just fancy way to say what's happening at the edges of the plate. So here's the boundary at x is equal to 0. So this whole little line is at x is equal to 0. So that's a boundary of the plate. And we have two boundary conditions there. One is we're saying that there's no deflection of the edge, that's not moving up or down, and there's no applied moment. We said all we have there is an applied stress, and we're not kind of trying to twist it or bend it at the edges. So what that means is that this equation here has to be satisfied, this one right here, when we substitute in this relationship. So when we put this relationship into that equation, so take two derivatives with respect to x, take two derivatives with respect to y, and then substitute in that x is equal to 0, does this in fact equal 0? Okay? it better, or otherwise this isn't a good guess. Okay. So we have another boundary here at y is equal to 0. That's this other edge of the plate that we're looking at. And here is the moment for that edge. So that would be this moment here, like that. The one over here would be a moment like that. And again, we're saying that that moment has to equal to 0, as the x does over here. And so in that case, we can't have any deflection, we can't have any moment, so this has to be true. Okay, and I think in one of the homework you're asked to kind of make these substitutions and prove to yourself that this function up here satisfies these boundary conditions, so that it's a valid function. And of course we have similar boundary conditions. We have two other edges. Here's an edge for y is equal to b, and here's another edge for x is equal to a. And on all four of those edges, we have to satisfy these boundary conditions. Okay? And again, you get to do that as a homework assignment. Okay. So what we're going to find out is that this is valid, that will work, those boundary conditions will be satisfied. So now what we have to do, like we did for the beam, we have to substitute this relationship into this equation. So now we're going to substitute this relationship into this equation, okay, and see where it takes us. So again, I think this is another homework problem for you to do. So here is the expression. And again, if you can take derivatives of signs, you can do this. It looks intimidating, but it really is pretty straightforward. So this first term just says to take 4 derivatives of this expression with respect to x, and then plug it into the equation there. For this expression, take 2 with respect to x, and then after that, take 2 with respect to y, and that becomes this expression. And then this one is just 4 derivatives of this with respect to y only, and then 2 with respect to x only, and then you get this big equation, and you'll be able to simplify it into this. Okay, so we're kind of giving you know the end point of that derivation, and this is it. So you have this big term in brackets here, like we did with the beam. We're able to factor out this expression here. And we know that in general, since we can pick any x and y value for the plate, that this was not going to be 0 in general. And that means that this term here has to be equal to 0. And you can kind of see it. This has the compressive stress as part of that equation. So here, just algebra, going to that point after setting this term equal to 0, we get this equation here. And then the lowest value of that, f sub x, we're going to give with the special name. We're just going to kind of define it here. That is the plate buckling stress, sigma CR. So the general compressive stress just turns into the plate buckling stress given by this relationship here. Okay. So we have a few more minutes. Let's just kind of look at what we've accomplished here. On the left-hand side here, we did a full derivation of a buckling beam because it was a simpler case that we could do fairly straightforward. And now we're following the same identical steps for a buckling plate, a 2D problem. Some of the equations are much more complex, but the analogy is kind of still there between the differential equation, guessing a solution, plugging in that solution into the differential equation. That gives us an algebraic equation, and for each we saw that this bracketed term has to be equal to 0 to be a true true to the physics. And then when we do that, we end up with a relationship that gives us the buckling stress. So that's where we're going to end this talk. We're going to kind of pick it up at this point because we're not quite done with having a nice compact equation for when will these thin wall plates actually buckle. Okay? We haven't totally solved that problem, but we don't have too much farther to go. And then what we'll do beyond that is start to actually apply the formula to certain situations in auto structure design. Okay? So see you next time for a little bit more on plate buckling.